Qualifying Exam for Algebra, August 2020, rings and fields, question 2. Let P be prime, let K be a splitting field of x to the 4th minus p squared over q. First part of the problem is finding the dimension of the splitting field as a vector space over q. And so, what are we going to do? Well, if our polynomial is x to the 4th minus p squared, we can look at this and we can factor it to get x squared minus p x squared plus p. So we have at least 2 distinct roots. And then at this point, we notice that this guy is irreducible over q, and this guy is irreducible over q, because by Eisenstein's criteria, we divide the last term, but the square of p does not divide it. So we have p divides p squared does not divide p. So we know that p of x is irreducible, or at least we can factor p of x into 2 irreducible terms as irreducible factors. Okay, so then if we were to factor p of x out fully, we get x minus root p x plus root p x minus I root p, and then x plus I root p. So we have at least 2 roots. Well, no, we have 4 roots. So we have plus or minus root p, and then plus or minus I times root p. So we can see that the splitting field, K, is going to be equal to Q adjoin I and adjoin root P, which this is 2 quadratic extensions. So that tells us that the degree of K over Q is going to be the degree of K over one of the extensions, Q join I, times Q of I over Q. So this guy is going to be 2, because that has a quadratic solution, or quadratic equation as its minimal polynomial. And then that guy also has 2. So our degree is 4. And then we need to provide a basis. So we're going to call it B, and our basis is going to be 1 I root P, yeah. Root P, and then I times root P is a basis for the splitting field. And that is part A. Yeah. Okay. Now if we erase this. And off this. Okay, so part B, we're going to look for the Galois group, right? Galois extension. Yeah. So we're looking for Galois, okay, there. And so then, what did I want my argument to be? Well, we know that the automorphisms have to send our roots to other roots. And so root P is going to have 2 options, plus or minus root P. And then I root P. It's also gonna have options, plus or minus I root P. So with that in mind, the whatever automorphisms we have, they have to align with this. So we're gonna have 2 times 2, or 4 automorphisms. And this guy is order 2. Order 2, no matter what you pick. This guy is order 2, no matter what you pick. So then our Galois group is going to be, how did I argue this? Before I argued it from there, and did I want to argue it from there this time? Because I'm not using it as a subgroup, I'm not. So it's just going to be Z mod 2Z cross Z mod 2Z. And then they want us to explicitly specify the action of each element explicitly. Yeah. So what we're going to do is, here we go. We have sigma. We're just going to send root P to negative root P, and then just I to I, and then we're going to have tau, which fixes root P, and then sends I to negative I, with the relationship that sigma tau sends root P, negative root P, and I, negative I. So what this means is that our Galois group Q, which has cardinality equal to 4, this relationship, well, like I already stated it. So now I'm just, I guess I don't need to do that anymore because I'm already stating what the Galois group is. So I don't need this. But these are the actions. Okay, and that's B. Cool.
And then on this part explicitly, why can't root P, for example, be sent to plus or minus I root P? How do we know it can only go to plus or minus root P?
The roots are transitive for the Galois group. Why can't it go to there? I don't know. The roots, because this one's a root for the irreducible x squared minus p. The other one is the I, this guy is the irreducible for x squared, yeah, plus p. And so they can't swap to each other's irreducible polynomials.
Right, thank
This
you.
guy's only covering x squared minus p and x squared plus p. Cool, great question. Okay, and then last part, drawing the diagram with the fixed fields associated to it. And I'll actually erase this piece. We're gonna have part C. So first up, we're gonna have Galois of the splitting field over Q. And it goes to the subgroup generated by sigma. And then we have the subgroup generated by tau. Both of those over the identity. Excuse me, and then adjacent to that, the Galois group fixes Q. Sigma does not move I, so its fixing field is Q adjoin I. And then this guy fixes root P, so we have fixed field root P.